Hello all, my name is Jan Homuth, Senior Application Engineer from Tasking Support. I hope you can hear me, and I also hope you see my screen. If anybody could just give me a short feedback with the chat. If my screen is visible, I would be happy. Okay, yeah. To see. Okay, thanks a lot for your feedback. So my screen is okay, my sound is okay. So let's start. So the topic today is screen is visible and sound is there. Thanks a lot for your feedback. I already had some other folks commenting, so everything is fine on that end. Let's start with our web session today. Little hands-on about how to allocate your application in RAM completely without using your flash. Normally the Tricore and the tool chains assign everything in RAM. And today you will learn how to play some tricks to get your application into the RAM only without using any flash. Our agenda today will be the following topics. First, I will show you how to set up a project in general. So with a little bit of code, just a little main routine. Then if necessary in the source code, if you want to use any attributes, we can touch that shortly, but with the way I presented today, we actually don't need to do much, but I'll show you some shortcuts there. The third item that we are going to see, that you are going to see, is to select the proper options in the linker, and that is important that you get these options right. Otherwise, you will end up with a bit of a mess that, well, you may have some flash in use and some stuff in RAM, but you don't know why. So there's some linker options that you need to select in order to really get your stuff into RAM and not use any flash. And the fourth item is also important. We'll spend some time with the linker script to select the right memories and to set up your linker script in a way that things are neat and orderly and also are located in the place where you actually want it. Because you may know, Tricores, especially the newer cores, RX1 and RX2, especially the RX2 TC39, they have an awful lot of different memories you can use. And you may want to have a little bit of control over where you actually put your code and data and library routines and so forth. We will have a look at that. And the fifth item that basically goes hand in hand with the development flow is that after the build, you will inspect the result in the map file. The map file is a very important piece of information you have, because the linker writes down each and every position of every section that your application has, that you have created. And you can control in high detail where this stuff actually ends up. But the map file may be a little bit hard to read, and you may want to know what to look for and how to search for the information that you lastly need to figure out if things have gone right or if something has gone wrong. The last topic will be Q&A. So if you have any questions, take a note, and at the end of the session, enter your questions in the chat, and I will try to answer them. If I cannot answer them immediately because the subject is too complex or there's too much of an in-depth explanation necessary, then I would suggest that I'll take my notes and we will follow this up via email through the support channel. I've seen this in previous presentations and webinars that some questions have come up that go beyond just a little 2-minute or a short explanation. And since our time frame is limited to half an hour, so exhaustive answers are not really what I can do for you, but as a follow-up via email through the support channel at support@tasking.com, absolutely no problem, that we can then discuss the topics that may come up on your side. So setting up a project, source code, linker script, map file. So I've already prepared a project. Just to give you an impression, if you don't know how to set up a project, we will do that shortly. Just as a demonstration how to get started with setting up a project, just get something basic into your workspace that you can actually build. So I've selected the TC39, and that is really a simple project. The source code you can see here is just one function, the main function with hello world, and just another additional function. So the way to get there is that you go to File, New, and then you select the Tricore C project. That's what you usually do if you want to do something for the Tricore, on the Tricore. As you can see, there are some other options here because there's not only one compiler in the tasking toolchain, but as you can see, it's 5. So it's an 8051 for the standby controller. Then there's an ARM compiler, a fully equipped ARM compiler for the high security module. Then there's one compiler for the PCP, which is the peripheral control processor of the older Auto series, TC17 and so forth, AURIX and Tricore derivatives. And then we have the MCSC compiler, which is for newer cores, AURIX1, with the GTM, which has the multi-channel sequencer, which is in short the MCS. That's a separate compiler because that's a separate core with a completely different instruction set that works basically independent of the Tricore core and does real-time arbitrary data processing of input data and output data and so forth. It's a very powerful core that allows to freely program input and output real-time processes within the general purpose timer module. So something that goes way beyond just having a little PWM or so. But we've got a compiler for that in there too in this tool chain. But right now we are going to stick with the Tricore project. We'll give it a name. I just say test hello. We'll choose a simple C project. We're not going to do anything with C++, not really necessary at the moment. So if you want to start a C++ project, you select that option, but we'll stick with C for the time being. And then, which is really important, that you have to select the right chip, which you want to use. You can see a whole array of chips way from the first TC1130, which is an industrial Tricore of the first generation. Then you have the Auto Future, and so forth. Derivatives are the TC72, TC82, 1791, and so forth, automotive chips. And we are going to use the TC39, which is one of the, how can I say, a larger, better equipped chips. It doesn't really matter, because whether you take an AURIX1 or an AURIX2, it doesn't make much of a difference for what we are doing right now. They just have different memory areas, more memories, and so forth. And just for demonstration purposes, I will use the TC39 because it's got the most memory and makes it easy to demonstrate why you should get a little bit of control over your memory allocations with a chip like this. Yeah. So we add the startup code, we add the linker script, and if you run on hardware, you also add the debugger synchronization utility, which is a piece of code that the debugger needs to deal with caching effects when setting breakpoints. That's automatically added if you tick that box. So the next thing and last thing is you select your target. So you have a variety of boards for selection, which are already supported and prepared. So you don't have to define your own processes in terms of debugger data and what kind of memories the debugger uses and so forth. So this is all pre-configured for you. There's a whole selection of boards. For this little test hello project, we're not going to use any hardware. We're just going to stick on the simulator because yeah, this is basically a demonstration of how to set up a project, basically set up for basic setup. So right now, what is important that you know that the properties is your entry point to the settings. And here is where you make all your settings. I'll go through the settings by means of the prepared project. So I'm just going to switch to my pre-configured project. And now we can go into the options. As you can see, for linking and locating the memories, so you're basically working on the locating side a little bit more because you want to have everything in RAM, but the rest of the code isn't too much affected. But there are some things that you need to keep in mind. For the linker, the default setting of the compiler is basically that an XML map file is generated. If you want to search through the map file, it's much better that you generate a text-based map file. This enhances your capability to search in the map file, which is a simple text file. You can do this in the IDE or use another editor. It's much easier than going through the XML viewer and go into the categories and so forth. So that's what you have to enable. I have also enabled the cross-reference informations and the processor and memory information. So I know that what the definitions actually are, which I'm using. And I have a better overview of the overall system and allocation scheme. For the sample, I have turned the optimization off. Normally, you have a whole bunch of linker optimizations here. I turned them off for clarity, so I know that everything that is actually being linked as object is in the project. You can save considerable space if you enable the duplicate data and duplicate code, and also you delete the unreferenced sections. That is normally a default setting of the compiler to immediately optimize it. But since this is a demonstration project, and since I want to know, or we want to know, what is actually all being linked for clarity, I turn these things off and I have no optimization effects, and I see clearly what modules and sections are in my application. So that's why I'm turning this off. It's a good idea when you get started with a project to turn the linker optimization off, and then at a later point you can decide whether or not you delete duplicate data, you delete duplicate code, and so forth. The allocation, the near variables are being turned off, and for the optimization, I also turn off the code compaction, because that leads to a couple of additional sections that you will see also from the library code, because the library code is compiled with code compaction optimization enabled. But I turn it off for clarity so that there are not some stray sections in my build that I have to take care of. Lastly, and the most important, is the linker optimization. Sorry for jumping across. The non-rommable. And that is one of the key points. The non-rommable option tells the linker not to use any flash memory. The definitions are found in the linker scripts that are provided with the compiler. So you have categories that are of memories that are being defined that are either RAM type, volatile memory, or non-volatile memory, as in flash or EEPROM memory. And that is one of the options that you have to use, because otherwise the linker will always try to allocate code and also ROM data, const sections, which consist of constants, which are not touched, which are only read. And the linker will place these in the programming flash, in pflash0, or wherever it finds flash type non-volatile memory. So that one is a key element to get your stuff into the RAM using the non-rommable option. As far as attributes go, for this particular setup, you don't really need attributes, but if you want to keep a function in the code and you want to avoid any kind of optimization, you actually want to keep it in there, even if it's not referenced or for whichever reason, you use the attribute used and protected. That's very important that you do this, because then you can actually force the function in there. In this sample, that's not really necessary, because that function is referenced here in main, so it is being called. Oops, it is being called, and therefore you don't have to protect it. But if you have a function that is not directly called, you can use the attribute. Take this out. I'll make a build now. And we will have a look at the map file. Which shows us a whole lot of stuff. As you can see, the TC39 has really a lot of different memories. And we are going to have a look at if there's any memory being used. What you can see is that the data scratchpad RAM 0 is being used, the SPR1 is being used a little bit, and LMU RAM is being used. But what you can also see is there is program scratchpad RAM being used, which is okay because it's there to execute code. The PSPR0 is used, but all the pflash, the programming flash, is empty. There's nothing in there, and that's exactly what we want. Yeah, emulation memory is not used. Data flash is not used, it's only reserved, but there's nothing in there. You can see it here, the summary, it's all zeros here. The usage of the DSPR actually is that comes from the startup code for each core. It uses a little bit of RAM. But overall, the goal is achieved. the application is completely in RAM only. All volatile memory units and no flash whatsoever being used. You have to keep in mind that the sizes are limited of the RAM memory, so there's only so much code you can place in there. But for smaller applications, it's perfectly okay to deal with that limited size of code. You get around 30, 40K or 50K or something like this. And that's perfectly okay for smaller applications, because usually you either want to test debug a smaller applications. Doing this with a larger application will not work. So you're not going to have like a megabyte or more of RAM available to put your application in there and run it completely from the RAM, because simply the space in RAM is limited. It's much less than the program flash size. Yeah. So we have achieved that. And if we scroll down further, the map file, you see a whole bunch of listings of sections, of debug sections. And one interesting part is here where you can actually see from specific modules where these sections actually come from. If you want to have sort of a cross-reference, this is the place to look for, because you see the section and you see the object, and you also see where the reference actually comes from. So that module calls another function or whatever, and that is being shown in a cross-reference here. That list is pretty long. Here we have the call graph. Interesting thing too, because you can see that main is being called. And you can also see that some additional function. Here's the call. And here you see it in a call tree. So the call tree can also be interesting for you to look at. And if we scroll further down, we will get a list of sections. And what you can see is that there are some descriptors in there. These sections are being named, they are being placed in a group, and that is done using the linker script. Again, if you go through that listing of the sections, you see that there's the program Scratchpad RAM, which is RAM also, and that there's the data Scratchpad RAM. So there's absolutely no pflash being used, and that what you see here, I've had some questions about that in the past. Oh, there's something in data flash 0, and that's only a reserved section. It doesn't actually use anything. And the boot mode header must be in the data flash UCB. You cannot do anything else. But the point is that the boot mode header here that you see in the map listing, that's only reserved. It doesn't actually use any space, because the default setting of a project is that only space for the boot mode header is being reserved, but nothing is written in there unless you change the option to say generate boot mode header. So here you see further listings, and further down you see the sections listed on name. And what's interesting here, you also have another listing of the symbols which are being sorted on address. And again, the memory areas are exclusively in the 7 range. It's all RAM range that is being used, and there's absolutely no flash being used. Now, looking at the linker script, you can see there's a grouping for the library code, which I've made just to get a little bit of order into the allocation scheme. And then there's the application near data. This is also a group, and far data. This is a group I've created, and it selects sections named app code. Now, this is not something the compiler adds by itself. This is something I have selected to do. in order to get my memory organized, you can see that the run address is DSPR0. So I have explicitly chosen to place this these data in DSPR0. It could be placed anywhere else, but for this example, that's DSPR0. And what you see here is that the text sections, which is exactly the code, text app code, is being placed in the run address for the program Scratchpad PSPR0. That's how it gets there. Now, how does this thing get its name? The compiler has an option or a pragma available that is called rename section. So when I use additional options for a specific source file, like here, then I tell the compiler on the command line, instead of setting, you can also do this with a pragma section all pragma in the source code. I give the compiler the renaming option to rename all sections to app code. That's a name I've chosen. You can rename it to anything, but that name must match what you are using in your linker script. So that's app code. And that's what you see also in the map file. Let's scroll up a little bit. Here we go. These are the ROM data that come from, these are the ROM data that actually come from the main.c source file. And then we also have the text.app code in the group application code as I have defined it here. Here's my group definition. It selects text.app code, and that name we get by renaming all sections of the module main.c to app code. So there is .data app code, BSS app code, and text app code and row data app code. Here's the row data. I add this group to the main group for the application ROM. So we have application ROM and a subgroup named application code and application ROM data. It's all being placed in PSPR0. If I select a different memory, it will be placed there. Let's try it out. I just changed the linker script. I make a rebuild. We are going to have a look at the map file. And it should be in there. There you go. You see that? That simple change has rearranged my application code from main.c into PSPR1, program Scratchpad RAM number 1, instead of the RAM PSPR0 that I've initially selected. Let's revert this, make another build. Let's see if there's success. Yeah. As you can see, there's a warning. I'll explain that later. So now we go back into the map listing, and what we can see is that the application code is in PSPR0 again after the build. The L file has been recreated. The linker has created a new map file report, and since I had it in the editor already, it's been refreshed, and now I immediately see the result of my changes. It's now again in PSPR0. There's one thing, you may see this warning. This warning is accepted and it is known. And if I look at the linker script, there is a note about this somewhere down the line, because the start label, here you go. The start label is one that has been hard-coded in the linker script. That is a label that you usually select. That is either fixed or determined by the processor linker script. And you can change it in the IDE. I chose not to change anything, but the reset address is something you shouldn't touch. And that warning here is explicitly copied into the linker script to make clear that warning, it is known why, and you can accept that warning. It's nothing bad, the application will work anyway. So, looks like we're already 5 minutes over time. I'd just like to have a look at the Q&A. There is one question: what is the advantage and practical use of non-rommable option? For instance, using volatile memory RAM for code sections. That's a good question. Pretty smart question, actually. One advantage can be that there are spaces in RAM that may execute faster than flash. RAM access is faster than flash access. So what you can do, but that's a different subject, you can selectively allocate code, for instance, for interrupt service routines that you want to take a speed advantage from. So that they are small, they have to run extremely fast because they're running in a high frequency, and you want to reduce the execution time of the interrupt service routine. Then you can locate this interrupt service routine in RAM, and it'll run faster than from flash, because physically flash access is slower than RAM access. That's one thing. Another thing is that the flash components on the chip only have a limited amount of read and write of write cycles. So you can only program the flash for a finite amount of programming operations. So you can do this 100,000 times or something like this, and then you see that the flash will degrade. There are certain limits on rewritability of the flash that are being documented with the TriCore. It's deep down in the documentation, and I don't really have the numbers in my head, but it's so if you run your application often and you reflash and reflash and reflash, you will hit a number of programming cycles where sooner or later the flash will degrade, and the chip manufacturer like Infineon will only warrant a specific amount of reprogramming operations for the flash. So if you do a lot of debugging, usually you don't count how often you debug a specific chip on a target board, but you just have to do it often enough, and then you find that the flash will degrade. So if you have small applications, you want, if you test them often, if you run them very often, you want to have these in RAM, because the RAM does not degrade versus the flash. Okay, Anonymous has another question. What is the difference between DSPR and PSPR? The DSPR usually is the data scratchpad RAM. That's the naming Infineon has chosen. That's basically the normal RAM for data. PSPR is RAM, which you can also use for data, of course, but that RAM is specifically designed to execute code. It's program scratchpad RAM. I said this before. The execution from PSPR is by nature a little bit faster. The access times are a little bit faster than DSPR. And also PSPR, the program scratchpad RAM, can be configured specifically for execution times. So execution time or execution speed for PSPR can be selected by configuring it to either match the execution speed of the flash, slowing it down, or running full speed. The data scratchpad RAM will not offer you that opportunity to influence how fast or slow code runs. So these are the basic differences. There are also some minor differences accessing across the various buses, but I don't want to go into the tri-core architecture in big detail. These are the main differences. You can use either one for either purpose, but if you want to squeeze out some performance, it's recommended to use the PSPR. Also, if you want to have fast executing interrupt service routines, you can put them into PSPR. In previous chips generations, RX1 and also the TZ17, you only had DSPR. There was no program scratchpad RAM. This has only been introduced later. And the DSPR was kind of a general purpose RAM that you could do everything with. And Infineon has decided to create two categories of different RAM with different application focuses. That's how I want to call it. So, any more questions here? I see that there are none. So, I'd like to thank you for your attention. And if you have any more questions regarding this, oh, there's more, okay. Okay, there are some more questions. Okay, is the code running from RAM protected from corruption? That depends on if you have any code or data in the data scratchpad RAM or in the program scratchpad RAM, there's no corruption protection. However, there is the LMU RAM, and that LMU RAM is ECC checkable. That means that the LMU RAM can be protected against corruption by applying an ECC check each time it's being accessed. That makes LMU RAM a little bit slower. However, in LMU RAM, you have corruption protection if you enable it. So if you choose to have any, for instance, calibration data or something like that, that you also want to store in an EEPROM, but where you want to keep a copy, which is corruption protected for your calibration of your application, and you absolutely want to know that it's not being corrupted, then you store it in the LMU RAM and you enable the ECC protection. The DSPR and PSPR do not have that kind of protection. If you want to protect it, you basically have your own checking routine to figure out if something's gone wrong with the content of these memory areas. On the LMU RAM, that is intrinsically done by the hardware of the tri-core memory unit. Are there specific concerns from Fernando? Are there specific concerns when running code from RAM in safety critical context, ISO 26262? Depends on your code. If you want to go absolutely safe, you can, as I mentioned before, if you want to go absolutely safe, then you can place it in LMU RAM. But there are no objections with regards to ISO 26262. Nobody tells you where the stuff has to run from. It's you as the user who has to make sure that the code that executes is safe. Where it executes from doesn't play a role. If you run it from DSPR and PSPR, so if you run code from RAM, you also have to take the precautions that RAM corruption is not possible. And of course, you will have to employ some kind of a power watchdog and shutdown mechanism that allows you to run code from volatile memory at all. But that is, I would say, that's a definition that you have to make in your application. And that has nothing to do just with the principle of executing from RAM. If you look at other systems that are being run, almost all the code is running from RAM and not from flash, and they are still certified. So, but there are mechanisms in place to avoid corruption, like from power conditions or something like this. So Haitam had not had another question, but so what is the question then? Let me see if there's something new. Q&A, chat. Okay, answered already. So we're about 15 minutes over time. I could also expect that. I thank you a lot for your attention. And if you want to revisit our webinar, you can actually look this up. We have the videos in store for you on the Tasking Resources website. Here are the resources. Here are the webinars. And that's actually where you find the on-demand webinars, the videos. Also, the webinar of today will be stored in this area. So you find it going through resources, webinars, on-demand webinars, and there are the videos for you. If you have any questions about the applications and the linker script, I will store this application in a download section for you, which we will publish along with that webinar information, and where you can download the project and review it for yourself. I'm aware that the run through the linker script and the options was a little bit fast, but if you can download the zip file and import that particular project into your IDE, you will have more time to review it. And if any questions come up, feel free to ask whenever you see something that doesn't make sense for you. So thanks a lot. Bye-bye.